So this is what it looks like. Here we've got a stain for normal myelin. So this is a section of the brain, and here's normal myelin, and here's the lesion here where the myelin has disappeared. When the myelin disappears, there's no myelin there for the stain to work on, so you see a very pale area. If you look in the blood vessels, so this is now a blood vessel, this is where the blood flows. All these tiny blue dots around the outside are the inflammatory cells, the immune cells coming into the brain. In this section here, we've stained for myelin inside the macrophages. So this section here, this slide here, shows the macrophages having eaten up the myelin. And this is what it looks like on an MRI. Here's the spot here of the damage. And I've just drawn a diagrammatic representation of the so-called active lesion here. The red dots are the axons, the green is the myelin, and these little blue things are the macrophages eating up the myelin. Now if we look at the chronic active lesion, so this is the next stage, the edge of the lesion here looks very much like the active lesion. So what it seems to be is that the macrophages eat the myelin and then move away from the blood vessel. If we look at the chronic inactive lesion, so again the next stage, here we see that there's complete myelin loss. So you can see in this area here, there's no myelin left. The oligodendrocytes are lost as well. There are no oligodendrocytes there. There are very few inflammatory cells. The cell is what we call, the area is gliotic, which what it means is that the astrocytes have made lots of glia fibers to try and patch up the hole to make the scar. But it's surrounded by normal appearing white matter. So the lesion doesn't spread over the whole brain, it just is limited to a small area. And the lesions are clearly hypocellular, there are no cells there. And this is what it looks like when we look down the microscope. Here, this is the stain for myelin again, so you can see the normal area of myelin, and this is where the myelin has disappeared. This is now a cross-section of a spinal cord, and again, the area of demyelination. And these are the astrocytes. They're starting to make all this sort of glue fiber to try and make the scar. There are hardly any cells in this area, and if you look at the axons, then the axons are damaged. So this is a stain for an axon. So these black stripes here are the axons. Now if we try and put this all together, there seems to be like a time frame in the development of the lesion. So here we have the axons again in red and the myelin in green, and this is a blood vessel. This is what it looks like underneath an MRI, so when in a scan. And here are the cells coming in through the blood vessel, eating up the myelin. So this is the active lesion. This is what it looks like under the MRI. This is the chronic active lesion, where the cells go to the edge, they eat up more myelin, and then they stop. And then this is the chronic inactive lesion when the myelin has disappeared. And the astrocytes make the fiber to make the scar. And this is what it looks like underneath the MRI. So using the MRI, we can actually see the development of the lesion. Now, if we put all this together, there seems to be a time frame in the development of the lesion. So the $64 million question is, what comes before the active lesion? So this is what my research is geared towards, is trying to find out what actually leads to the active lesion.